Okay, now that we've given out a lot of hints for the exam, we will now proceed with the next chapter. Our story today begins in the book of Acts. Actually, we'll get to that in a moment. Couple of things that you might encounter in biochemistry having to do with electrophilic aromatic substitution. One is the biosynthesis of vitamin K. So that's shown here. And it's got this long hydrocarbon chain, and that hydrocarbon chain is attached to an sp2 carbon of an aromatic ring. And that reaction is basically a Friedel-Crafts reaction. The leaving group, so here is the long chain. It's basically an alkylation. Here's the leaving group. It's a pyrophosphate group, which we could talk about as not really, we'll get to it later, not really important for our discussion today. But the leaving group leaves to give a carbocation. Notice that that carbocation would be resonance stabilized because that's an allyl leaving group. And then the carbocation gets attacked by the aromatic ring. You actually get biology to do the Friedel-Crafts reaction in between two groups that are already meta to each other, which you've been told not to do in synthesis, and that's true, but this is why we have enzymes. In any case, removal of a proton and re-aromatization gives you vitamin K. Another biological example of an electrophilic aromatic substitution reaction is the preparation, biosynthesis of iodotyrosine. Tyrosine is an amino acid that has a phenol side chain. And in making thyroid hormone, you need to start putting iodines at the ortho position relative to that oxygen. Notice that on the aromatic ring of tyrosine, you've got this OH group, which is a strong activating group and is also an ortho and para director. You have a alkyl group, which is also an ortho and para director, but it's not quite as strongly activating as the OH group is. The electrophile here is probably a weird compound you haven't seen before, a bond between an OH group and iodide. You get that from an enzyme that oxidizes iodide anion with peroxide to give this IOH compound. And then it's electrophilic aromatic substitution as the ring attacks the iodide. OH gets protonated perhaps as it leaves to be a good leaving group. And you end up with the iodide ortho to the OH, which is the more strongly activating group. So a couple of places in biology where this kind of thing shows up. I just wanted to give you some examples. Yeah?
Do you know how radioactive iodine works then in like thyroid cancer treatment?
Radioactive iodine works in, how does radioactive iodine work in thyroid cancer treatment? No, I should. That's an interesting question. My guess is that, I'm hedging, some of you probably know this. Thyroid hormone, is that actually made in the thyroid?
No.
Nobody knows?
It's made from iodine and
Right, no, but is it made in the thyroid?
no, it's made elsewhere.
Okay.
And then it goes into the bloodstream, which is
Well, so if it were made there, then you'd just be targeting radioactivity to the thyroid gland. If the target of thyroid hormone is in the thyroid gland and that's where it binds, then it's the same sort of thing. The radioactive molecule binds to the location. I'm sorry, I don't know more about it. That's a fascinating question, and you got me. Dang it. Oh well. There's lots I don't know, so keep asking it. All right, others? Oh, it's Memorial Day weekend too. I wonder how many of you took the exam and then skipped town. Anyway, I don't blame you. Okay, so our story now for the first part of today is going to start in the book of Acts, chapter 16. Paul and his missionary companions want to go into Bithynia, but Paul has a vision, and there's a man in Macedonia saying, "Come over and help us." This is chapter 9 in Acts 16. And so they follow the instructions of the vision, follow what the Spirit tells them to do, and end up in Philippi, which is the major city of Macedonia. And in verse 14 or 13, on the Sabbath we went out of the city by a riverside, where prayer was wont to be made, and we sat down and spake unto the women which resorted thither. It's a great King James word, thither. And a certain woman named Lydia, a seller of purple of the city of Thyatira, which worshiped God, heard us, whose heart the Lord opened, that she attended unto the things which were spoken of Paul. Lydia, a seller of purple, small businesswoman, and actually pretty probably prosperous small businesswoman, because she's selling purple cloth, which was really, really expensive back then. Purple was the color of the wealthy and the royal. Here's the molecule probably that Lydia was using to dye purple cloth, or somehow trafficked in this. Maybe somebody else was isolating the molecule and then she was using it to dye the cloth. Perhaps she just sold the cloth. This is called Tyrian purple, and this is isolated by grinding up a Mediterranean sea sponge. So highly conjugated, you can see, and this molecule has a purple color. This is how you used to make purple cloth. If you are wearing something that is purple today, it probably does not come from Tyrian purple now. Purple is no longer the color exclusively of the wealthy and the privileged. And the reason why that is because of chemistry. So I want to tell you a story about colorful molecules, and it has to do with some of the molecules you'll encounter in chapter 22. I will say at the outset, by the way, chapter 22 has a lot of review stuff about amines. Please look at it. You're welcome to look at how amines are made. There's some stuff in there about which nitrogen is basic, using things that we've talked about so far, so we're not going to review that. But we're going to talk about the new stuff, and a story of sort of molecules that are colorful illustrates a lot of interesting chemistry. So, in the mid-1800s, 1856, a British 18-year-old, W.H. Perkin, was doing chemistry in his house because at the time, if you had a little bit of money and you were British, chemistry was fashionable to do, I guess. People like to have labs. He was trying to make an anti-malarial compound named quinine, and he was hoping to start with a molecule that you've seen before called aniline. His approach never would have worked, but he didn't know that. And he also didn't have a lot of the analytical tools that we have nowadays to confirm that we made the right stuff. His compound, his starting material, aniline, was not pure. It was actually contaminated with these two other molecules. One is called orthotoluidine. This is the orthoaniline version of toluene. You've got the methyl group on the benzene ring. And then the para version. Why was it that these weren't pure? Probably because at the time they were separating these compounds by distillation, and they had similar boiling points, and so you just couldn't get it 100% pure. So Perkin's strategy for attempting to make this anti-malarial molecule quinine was to use oxidizing conditions. So this is potassium dichromate, and this is sulfuric acid. You may have seen this reagent before in 351 when we talked about oxidation of alcohols to carboxylic acids. CrO3 is an alternative reagent here, but potassium dichromate does the same thing. And he got every chemist's nightmare, which is a tarry black solid at the bottom of his reaction. And this usually means that you failed. If you are in a highly wealthy funded lab, you just throw the flask away and you move on with your life. He was doing this out of his house, so he decided to let's try to clean it out. And so he started rinsing the flask with alcohol, hoping that maybe it was, non-polar, or what was in the flask would dissolve in alcohol and he wouldn't have to scrape it. And boom, purple. The alcohol rinsed something that was purple out of this chunky black solid. That was 1856. In addition to thinking, ooh, that's pretty, he thought, ooh, that's useful. And so he immediately patented it, saw that it would be useful for dyeing silk and textiles. The next year he had opened up a factory. Within 18 years he had retired, a wealthy man at the age of 36, having discovered a purple dye that now could be used in the textile industry. There are still samples of his purple dye available today, and cloth that was dyed with the purple sample. What he actually made was a mixture of highly colorful compounds. This is one of them, and this is way more complicated than the starting material that he had in hand. And I don't think even during his lifetime that they sort of knew what the structure of the molecule was. Figuring out its structure came with modern analytical tools. But if you look at the structure, you can see some of the starting materials that are present that were present in his mixture. You've got aniline, orthotoluidine, paratoluidine. So look for ortho and para relationships between carbons. As an example, this section must have come from orthotoluidine. This section must have come from paratoluidine, and these two, which lack sort of carbon substitution on the benzene rings, must have come from aniline. There's a lot of linkages in there that are kind of strange, and the actual chemistry is not necessarily that important, though it does illustrate some electrophilic aromatic substitution. This molecule's purple, and as I said, there are others. I'll just show you FYI, not so you can worry about it and not so you can encounter the mechanism of this reaction on an exam, but just for your information. They think that what's going on is that the oxidizing agent removes an electron from aniline. You get what's called a radical cation. And another electron is lost, and then you get this basic electrophile. It looks like an imine and an alkene. It also sort of looks like an alpha-beta unsaturated carbonyl compound, only there's now gamma-delta unsaturation as well. But this molecule is a good electrophile, and what they think happened is that you did electrophilic aromatic substitution using one molecule of aniline, attacking the electrophile to make a new carbon-nitrogen bond, and then removal of the proton at the carbon where the nitrogen was at resulted in re-aromatization, and that maybe made one of the bonds in this movine A type molecule. All right, so that's sort of accidental chemistry, making dye molecules, and it probably involved some electrophilic aromatic substitution steps. But about the same time, so this discovery spurred a whole industry, a whole chemical industry, especially in Germany, for identifying molecules that were colorful. And German chemists discovered a whole class. Okay, the computer's running without juice today. I gotta run upstairs and get my plug at some point. We'll see how long it lasts. Let me know if it goes to sleep. German chemists discovered a whole class of colorful molecules that were called azo compounds. And azo, I think, is from a Greek word, but it's used to describe compounds that have nitrogen in them. So this is an aryl azo compound, and this here is a diazo functional group. And we're going to talk in this chapter about how to make this functional group and how to make molecules like this. A lot of azo compounds, as you can see, are highly conjugated. Highly conjugated molecules often have a HOMO-LUMO gap that is in the range of visible, in the visible spectrum, and so they absorb visible light, and therefore they appear colorful. And so there are a lot of these molecules that have interesting colorful properties. There are a couple of them, for example, that are red. So all of these are going to have the same. And I promise not to ask you which of the following molecules is red. That's sort of not a fun question. But here's one that's called para-red. You've got benzene rings on either side. One of them is nitro, and then one of them has a second benzene ring attached to it. And this is a red dye. And you can do a lot of sort of elaborate things to generate interesting, colorful molecules. I'll just show you, just so you can get a sense for how elaborate some of these structures can be. All right, so this one's got two azo groups, and on either end is the same thing. You've got two benzene rings fused to each other, and then some functional groups coming off the benzene ring. This sulfonate group on this side, and then we're actually going to have another of the same molecules on this side. Nope, I think I did it wrong. Oh well. That's close enough. Nope, sorry. Changed my mind. Obviously, I'm not going to have you like, oh, you have to memorize this structure. That's not useful, and that's not what we're about. This structure is called Congo red, and it's a dye that is still in use today. So why do we care about colorful molecules? Well, obviously, you've got the textile industry, and having colorful clothing is popular. But it turns out that there's an intersection between the German dye industry and the whole field of cancer chemotherapy that is pretty important. So German chemist Paul Ehrlich was working with a strain of bacteria, and under a microscope, sometimes it's difficult to see things if you're just looking at a normal light field image, and so sometimes it's useful to distinguish compartments of various cells and distinguish one cell from another by putting some kind of dye on the cells. And Ehrlich noticed that certain dye molecules stained some bacteria selectively, which was really weird. And it gave him the idea that there were some molecules that could be selectively taken up by bacteria, and because he could see that the dye was being internalized into the bacteria, and that led to the idea of, well, could I invent a molecule that if it's taken up selectively by the bacteria, could it selectively kill bacteria? And so this led to the whole idea of targeted therapy, antibiotics, and anti-cancer therapy. So the first dye that was used to kill bacteria was made by a German company, and the molecule is called Prontosil. This happened in 1935, and the German chemist was working in a dye company, and his daughter got a streptococcal infection, and he did something which you're never supposed to do, which is decided to test a molecule he was working on her. There's all sorts of things about internal review boards, and if you want to do experiments on vertebrates anymore, you have to get all kinds of permission. It's unethical to, but all of this was not worked out at the time, and he just wanted to try to save his daughter's life. This is the molecule Prontosil. It's an azo dye, but it had also been shown to inhibit bacterial growth in mice. And his daughter actually recovered. She should have died, and she didn't. And so he lucked out. Again, you never, please, learning from history, you never take stuff home from the lab and inject it into people. There are ways to do chemical research that's safe now, but this led to a whole field of antimicrobial, antibacterial drugs, and only 4 years later, in 1939, he won the Nobel Prize in Physiology and Medicine. When chemists discover a lead molecule, they often ask which part of the molecule is important for its activity. And it just so happened that the portion that is important for its antimicrobial activity is this portion. And that's called the functional group here is called a sulfonamide. And the active antibacterial agent here is, for some drugs, is not actually the molecule that's administered itself, but a metabolite. And this is the portion of the molecule that is active as an antimicrobial agent. And this led to a whole class of molecules, which you can still read about, called sulfa drugs. There are a few others that sort of came out of the German dye industry. One of them is elaborate enough that I should have just copied and pasted rather than attempted to draw for you. But what the heck? It is like Congo red. It shares this, what's called a biphenyl core, where two benzene rings are linked to each other. One of those biphenyls has a sulfonyl group on it. There are two azo groups on either side of the biphenyl. And then there's these really elaborate rings on either side of the azo. I'm trying to make sure I get this right, and I've already gotten it wrong. And again, sorry for wasting your time drawing this structure, but it's interesting just sort of how elaborate some of these things can be. So this is called trypan red, and it actually is used, it can kill trypanosome parasites, and those parasites are responsible, I think, for sleeping sickness. And then sometimes if you look on the periodic table, things that are 1 or 2 rows down in the same column can have similar activity. Some chemists ask the question, what if we try to make an azo molecule but we use arsenic instead? And so here is the arsenic version of an azo molecule. Looks just like the azo molecules we've talked about, only you've got arsenic there. And this is actually an anti-syphilitic molecule. At one point, it was the most prescribed molecule in the world. And sort of the advanced symptoms of syphilis are terrible, and so this has spared a whole lot of pain. So what you're seeing is that chemists have always been interested in molecules that are colorful, and often the idea of colorful molecules has led to molecules that have other interesting properties. And the fields of cancer, chemotherapy, medicinal chemistry, the idea of what if we change some functional groups out here, what does that do to the color and the properties of the molecule, all can sort of be traced back to this area. All right, so that's our long story. I've already told you most of what I know about this story, but I'm happy to entertain questions if you want to try to stump me. Good. Are sulfa drugs still used widely? That's a good question. Do you know what my superpower is? It is Googling. Yes, though it looks like mostly urinary tract infections and infections in burns. I'm not sure what the mechanism of resistance is, or whether yeah, I mean, it looks like there's some, if they're not as widely used, it looks like it's possibly just due to adverse reactions and that there are just better drugs available now. Others?
I was just going to ask if you knew whether we still use parts or principles from Kirkman's mechanism to make purple dye?
Do we still use that to make purple dye? I don't actually know. A lot of the yeah, it's a good question, and not sure. Okay. All right, so let's just learn a little bit of the chemistry that can be used to make these azo compounds. Some of it's going to seem straight out of chapter 20 or whatever on electrophilic aromatic substitution. You actually start with an aniline, and then we're going to introduce a new reaction today, which is called diazotization. This is one of those words that doesn't explain anything, because it simply says we're going to add a diazo group to a benzene ring. But you put ation at the end of it, and it sounds great. It's like a whole class of medical terms which a doctor will say, oh, you have this, and all it does is describe your symptoms back to you, which is always kind of fun. So the conditions for running this reaction is going to be a reagent that you haven't encountered before, sodium nitrite, that's NO2 rather than NO3, and HCl. Yeah. Must have gone to sleep. Still recording, and there we go. All right, when we take a break, I'll run upstairs and get the wall adapter for my computer. It keeps doing it? Why? Still got plenty of charge. Still recording, still good.
Dr. Price, do you want to borrow mine?
I mean, that's not, will it work?
Is it right?
We can try. Yeah, thanks. If I've got a... Oh, I heard the ding.
Gone?
Yep, we're good, thank you. That's not the only time someone from the audience has tried to save me. The other, well, it's been years now, but I fidget a lot, and sometimes when I'm talking, and the tip of the Apple Pencil can come unscrewed. And I was one time fidgeting with it, and then I dropped the tip of the Apple Pencil, and it bounced and went back into the computer here, and I couldn't get it. And somebody actually lent me one from the audience, which was really nice. So this is good, though. This is less embarrassing, I suppose. Right, so diazotization, we've still got the screen. This will convert the aniline to this what's called a diazonium ion. And this is a reactive intermediate. This would be an aryl diazonium. And you can tell that it's a reactive intermediate because you've got something in there that looks a whole lot like it could leave as N2 or nitrogen, which has got to be the best leaving group there is. There are other kinds of diazonium molecules, but in general they're not that stable. The aryl diazoniums, however, are stable enough to deal with as intermediates. The question everybody wants to know at this stage is, what kind of group is this? Is this an ortho-para-director or a meta-director? And the answer is nobody does electrophilic aromatic substitution on the aryl diazonium molecule, probably because it's not stable enough. So actually, if we do electrophilic aromatic substitution, we're not going to do it at this stage. We would either do it before and put groups on the benzene ring before we do this process, or we might do it later, but not at the stage when this diazonium group is on the ring. The mechanism for the reaction is known, and I've got it here in my notes. I don't know that it's that useful for you to know. I'll draw the Lewis structure of the NO2 anion. Under acidic conditions, you can see how it would be probably pretty reasonable to protonate the negatively charged oxygen. And probably under strongly acidic conditions, you can see how you could convert that oxygen into a good leaving group. Then it would be a simple case of kicking off a good leaving group to get to the key electrophile here. Which you can draw as this resonance structure as well. This is called the nitrosonium ion, and it is your electrophile in the diazotization reaction. Basically, you make the nitrogen-nitrogen bond comes from attack of the aniline nitrogen on the nitrosonium nitrogen. And then what happens next is a lot of tautomerization, and ultimately the oxygen comes off as water, and that establishes the double bond. I could show you all of that. I don't intend to ask you a question about it on an exam, and my guess is most of you are content just to say, okay, that's fine. If you're not, come talk to me. I can show you the mechanism. It's not that hard. It's also not that interesting. So, aryl diazonium molecules are electrophiles in two interesting ways. The first way in which they are electrophiles is a new way that you're not used to with benzene rings before. So let's talk about what you can do with aryl diazoniums. One thing you can do with them is called basically nucleophilic aromatic substitution. I told you that the nitrogen, the diazonium ion group, is an excellent leaving group, and it is. Under such situations, it's possible to do a substitution reaction, where, for example, OH minus replaces the diazonium group. However, the mechanism is not SN2. You learned a long time ago that you can't do SN2 for aryl leaving groups because SN2 involves backside attack, and you can't get there from here. You can't get to where the sigma star is. So what's thought to happen is an addition followed by elimination step, which looks like this. Oxygen attacks the carbon that has the leaving group on it. You would get an intermediate that looks like this. And that intermediate is stabilized, the negative charge is stabilized by resonance, and then it collapses and kicks off the leaving group, thereby restoring aromaticity, and you make nitrogen, which is of course a fantastic leaving group. So that's one of the things you can do with the diazonium ion. This is called nucleophilic aromatic substitution. And to some extent, you can pick and choose your nucleophile. A lot of different things you can do. This is the first time we've ever been able to make a phenol, so that's kind of interesting. We've used that all the time as a starting material in various synthesis reactions in chapter 20. But you can take the same starting material, the aryl diazonium, and then sort of change what the nucleophile is. So your text points out if you use copper chloride, the copper actually must be significant, because otherwise you just go cheap with sodium chloride. Your text doesn't explain what the copper is doing here, so I don't really have an explanation for you. This is one way you can make the corresponding iodide. We didn't really have a halogenation reaction to make the iodide, so that's an interesting example. And then it turns out there is, let's see, I'm going to get it wrong, aren't I? Oh, there it is. There's a reagent that you can actually use to install the fluoride. It's not sodium fluoride, and again, it just must not work well. This is a strange reagent, HBF4. If you try to draw the Lewis structure for HBF4, this is sort of what you come up with. What this is kind of in the same way that sodium borohydride was a hydride delivery reagent. This is a fluoride delivery reagent. F- is the nucleophile. It's probably handed off directly from the boron to the carbon. All of these are going to follow this similar mechanism with the negatively charged nucleophile being delivered to the carbon that has the leaving group on it. But these are sort of convenient ways for making aryl halides. Of course, you know, for the chlorides and the bromides, we've already got ways to do that via electrophilic aromatic substitution. But the iodide and the fluoride, these are things we haven't had a way to make before now. So they're interesting from that perspective. Okay. Yeah.
How does the fluoride attack if it doesn't have a minus charge?
It sort of does. How does the fluoride attack if it doesn't have a minus charge? It sort of does. So you can see in that structure the negative formal charge is on the boron. But remember, formal charge is simply about counting electrons. It does not change things like electronegativity. Fluorine is still more electronegative than boron. So most of that negative charge has to be felt on the fluorides rather than the boron. So what likely happens is just this. Okay, others. Okay, so that's one example, that's one kind of thing that aryl diazoniums can do. Now let's show you another. Aryl diazoniums can be electrophiles, can be the electrophile in electrophilic aromatic substitution. So, here is an aryl diazonium. Oops, I put the formal charge in the wrong place. There we go. This diazonium salt is also electrophilic on this nitrogen. In the same way that a carbonyl is electrophilic, a protonated carbonyl, an oxonium ion is electrophilic on the carbon. I could draw a resonance structure of the aryl diazonium salt in which I had a positive charge. No, that doesn't work out, does it? There we go. Sorry, too much. Yeah, on the terminal nitrogen. And in that case, what we're going to do is very similar to a Friedel-Crafts reaction or a Friedel-Crafts acylation reaction. We're simply going to have electrons from benzene attack the nitrogen. If we attack this resonance structure up here, we push arrows onto the nitrogen. That creates a new carbon-nitrogen bond with my second benzene ring. So there's the new bond that I made. And then we're going to have that sort of familiar situation we saw with electrophilic aromatic substitution. After the fact, some base, and it doesn't need to be a strong base, even a very weak base, will re-aromatize. And that gets us to the indicated diazo compound. All right, that's called, sometimes this is called a diazo coupling reaction, and it allows you to take a benzene ring that you've made one way and to attach another group that you've made an entirely different way, and now you can have two molecules pieced together. And if you go back to the types of dye molecules I was showing you in the beginning, this is kind of how they did that. Okay, questions about that diazo coupling reaction? All right, that's a good breaking point. We're going to practice synthesis next, and then I think we'll probably move on to chapter 23. Chapter 23 is about peptides and proteins. It's chock full of stuff. There's more we could do there. We could stand a little bit more time on there than just one lecture next time. So let's take a few minutes and we'll get started again.